Hi, everybody. Thanks for coming out. Hopefully you're having fun. And hopefully you won't scream and cry. I noticed that when Alex said you have to have HTTPS for service workers, and when Adrienne said all the cool new APIs need HTTPS too, I'd like to thank you all for not screaming. Maybe you screamed inwardly, but I really appreciate it, because a lot of times they're screaming. So I want to help you find out how to reduce the screaming. And the good news is we can. So first, I'd like to pitch why you need TLS. So I'm going to be focusing mostly on the performance aspects, but first I should motivate it. So as you may know, Chrome has the three goals of speed, simplicity, and security. And I'm on the Chrome security team, specifically the secure usability team. But all those things have to go together. We can't have an easy, fast path to crash into the wall. We can't have terribly slow safety. The safety can't be too complicated. So unless all those three things are working in harmony, we and our users are going to be really sad. So I'm going to try to combine them in a way that works well for everyone. So why do you need TLS? I'm speaking today to you as website developers, and I want you to think about the needs of your users as well. So your users care about the data that they're storing in your application. If your application matters at all, then it matters to people who care about the privacy, the correctness, whether or not it's been mangled in transit. Even if it's just a news site, it matters that they're seeing the true news. And sometimes the news gets falsified, and it really does happen. For example, the AP's Twitter account was hijacked a while back and caused a 2 seconds long huge dip in the value of some stocks because of a false tweet that was sent out. And someone made a lot of money in those 2 seconds. And so we want the news to be true so that that kind of thing has less chance of happening. So any app, even the simplest just publishing facts app, should be safe. And if you went to all this trouble to animate your UI nicely and to have cool graphics that fit a material design specification or whatever it might be, you went to a lot of work. And you want your users to see the true work that you've done. Unfortunately, when we don't use a data channel that provides authentication and data integrity, people between you and your users can mangle that experience. And in fact, mangling the user experience is other people's business model. Messing with your business model is someone else's business model. Here's an Ars Technica story about how Comcast is doing that for their own gain. So if that little thing appears over your nice animations, your users aren't going to have a good experience. So you want what you built to get to people. You also want your privacy policy to have any meaning at all, which requires the basic bare minimum of security that TLS provides. If you're monetizing your site, and I hope you are so that you can all continue to have food and rent, either people are paying for it directly, and obviously you need to secure people's payment instruments, whether it's credit cards or PayPal or whatever. Or if you're monetizing by ads, you want to monetize your ads and not the ads that random people are inserting, which incidentally is a business model. So here's a person on Stack Overflow asking, I'd like to monetize, I'm giving away Wi-Fi, and I want to make some money on it. How bad would it be if I took people's AdSense IDs and put in my own? Would I get in a lot of trouble for that? And obviously the answer is, what the hell, man? So, but people are doing that. People want to do that. When I've given forms of this talk before, I used to show, I was at a free Wi-Fi cafe in Austin, and they were inserting all sorts of goodness on the front page of Google, including enticing me to download software, which was possible back then. This is many years ago when Google search wasn't on HTTPS. And so people have been doing this for a long time. It's a stable strategy, so we should all get together and make it not a stable strategy. So TLS is good. It's good for you. It's good for users. It's good for your business. But let's get to the performance part, because it's a big concern that people have. Is this going to kill my speed? We've talked about we want rendering to be fast. It has got to be paper smooth. And if TLS messes it up, then I'm in trouble. So let's figure out why not. So HTTP 2 is the new fancy HTTP version. It's coming up. We've built previous demo versions of it before. You may have heard of Speedy. Google is using it for lots of its sites. Chrome supports it. I think at least one other browser does. And HTTP 2 is being standardized. And we've experienced great results, speed improvements when we turned on TLS. And there's important reasons for that. So the first web was for documents, HTTP 1. HTTP 2 is about applications, and it's tailored to the needs of dynamic applications like real appy apps on the web. So that requires that it perform very differently on the network than old-timey document-based HTTP. So HTTP 2 brings a couple super important features to make apps responsive on the internet. One is multiplexing. So if you think about HTTP 1, you have this nice feature where you can establish a TCP connection, and then you say get / and then they give you the answer. And if you want to save the cost of having set up that TCP connection, you can send another get or another post or whatever. And that's very cool, and it helps. But we need more than that for these super responsive, modern 2014 apps. So for that, we have multiplexing in HTTP 2, where you can, it's kind of like, in a sense, it's kind of like streams within a stream. If you ever heard of SCTP, it had a similar idea. So you can, once you set up your HTTP connection to a server, your HTTP 2 connection, you can interleave requests and responses at all different times over the same connection, and it can live really long, and it can be sending tons of stuff. Not even simple documents, but constant streams of video streaming interleaved with your get the icon, get the avatar, post a comment, all happening on the same HTTP connection. So that's a huge, sort of like a huge improvement over mere pipelining and mere persistence. It also solved this problem where over one connection, you really need to get that CSS file to style the page, but you're waiting for the JPEG to come, which you asked for first. And so until that JPEG comes, you're not going to get any CSS, and there's going to be that like style jank where it suddenly, the style appears too late. So the head-of-line blocking problem is a big problem on networks, and HTTP 2 does its job to deal with that at the application layer, and it's super important. Another important thing is that you can, the server or the client, whoever initiates a stream within the long-lived persistent connection, can tell the other side how important that stream is in among all the other streams that are currently running. So a server can say, hey there, client, here's the main web page, and now you're going to want to focus on this JavaScript file. It's super important. It's jQuery, and we can't do anything without that. And you'll need the CSS next. And all those avatars for all the users, those are important, but they're third. So don't get those before you get the JavaScript, because it's really important to have the JavaScript. And then the client can prioritize how it handles the incoming packets, and you can get a much lower latency page load, a much better user experience. And either client or server can initiate a stream. You can say like, hey server, I'm sending you up some updates. Say it's a mail application. It's really important that you process these emails that I'm posting before you process the IMs. Maybe the emails are more important, or vice versa, whatever it might be. So that's super, super cool features. And then as a minor sort of bonus, HTTP 2 compresses the headers of HTTP requests and responses. In the old days, you could compress the bodies, but sometimes the headers would get big. If you have like millions of cookies or just huge lists of options and you keep repeating them, sometimes it could be nice to compress those, so now we can. It can be useful. But all of that goodness only works on TLS. There's two reasons for that. One is we really want the future web to be safe so that it can be appy. if you think about your mobile apps, and even Windows and OS 10, but certainly iOS and Android, all of those apps pretty much have to be these days signed. Like you can't get into the Android store without your developer key. You can't get into the iOS store without your developer certificate, so that people can believe that they've got the real app. Well, if we want to have that same goodness, HTTPS is that. TLS is that for the web. But the second reason that relates to performance is that we need to have end-to-end reliability to deliver all that goodness, all those multiplex streams and the header compression. We need for our communications between client and server to be opaque to all these meddling middle boxes, all those people who want to insert their own ads into your stream. They're also doing things like, oh, I'm going to optimize your site for you by stripping out some of your headers. It looks kind of big. I'm just going to get rid of those for you. Well, maybe you needed those. Maybe your app depended on that. Or maybe they're going to say, oh, I'm just going to downscale all your images. It's better. Trust us. And the users are like, why does everything look so fuzzy? Or whatever. Or there's passive eavesdroppers. Mean time to Snowden is 11 minutes. Passive eavesdroppers, active tamperers who are not messing with your traffic for the purpose of inserting ads, but maybe inserting spamware, adware, or fraudware or spyware. All those sorts of things can happen, whether they're for nominally good reasons or for nominally bad reasons. We don't even need to worry about that. The fact is, HTTP2 looks so different on the wire that all of those middle boxes that are expecting to see HTTP1 will do the wrong thing when they try to help by mangling your traffic. So we know from experience that it's really, really hard to get a successful HTTP2 deployment over not TLS. Over plain TCP, all sorts of breakage happens. So we need the reliability. If you think about it, inside a computer, you've got your USB wires and your PCIe. Well, we're building a planet-sized computer, and the message bus is all the air, all the copper, and basically anyone could be messing with it, and they are. So we need the basic safety that TLS provides. In fact, this argument has been going around and around since the very beginning of the internet. If you haven't read it yet, you should read this great paper by Jerry Saltzer from 1980. I think there was drafts of it in 1979. And he's trying to define what he calls a careful file transfer application, which is basically what we're doing here, HTTP. And he says, so if you were going to try to build such a thing, you'd want the server to tell the client, here's your file, and you want the client to have some reason to believe they got the full file with no damage. How would you do that? You could build reliability stuff at the ends, or you could try to build reliability stuff in the middle. You could have the telephone network try to make some kind of promise of reliability, or something like that. But instead, he argued that the place to put the reliability guarantee is at the endpoints. And any reliability guarantees that happen in the middle, or if you will, at lower layers in the network stack, those are nice optimizations if they work, which is not always. So if you really care, do it at the endpoints. And that's, again, that's what TLS gives us cryptographically. It cryptographically gives us server authentication, data integrity, and data confidentiality. What we mean by that, when I say cryptographically, what I mean is that it would be computationally infeasible for one of those middle layers to get away with messing with your stuff. They could, but it might take more energy than there is in the sun, so we'll call that good, hopefully, if the cryptographers have done their job right, and they usually have. They're much smarter than me. So really, security and reliability are kind of the same thing. Security is reliability even when people are purposefully messing with you. Reliability is like, oh, there's noise, and there's bad weather, and lightning strikes caused that server to go down. Bummer. Security is when it was not a lightning strike, it was a bomb, or some crazy person inserting their own ads. So, and since the message bus is the planet, we must and should assume that we're always under attack. So, but this all sounds good. I want to have all those nice benefits of HTTP2. I want to provide safety to my users. I want my privacy policy to be true. I want people to feel good and happy and safe when they're using my app. But I've heard that TLS is really slow. Isn't it really slow? How can we fix that? So there's several shades to that of answer to that question. If you think of it not as a Boolean, but as like an 8-bit wide answer, the high order 6 bits are all no, it's not slow. And the low order 2 bits are, well, we could probably tune up a couple things. So my colleague, Ilya Grigorik, has a cool website, which if you haven't seen it, you should visit, that expands on why all those high order 6 bits are 0. It's called istlsfastyet.com. And the answer is yes, except we need to get more people using it. So, and he's also got a really good book about optimizing those last 2 bits. But let's think about making sure that TLS always fits into our performance budget. If we want to say we have 1,000 milliseconds before people will get bored and look away, we've got to make sure we meet that deadline. So let's do what we can to make sure that TLS is not the thing that breaks it, right? So the first thing to do is optimize the higher layers first, the content layer, the HTTP layer. And HTTP2 is all about building in a lot of those HTTP layer optimizations into the protocol so that you don't have to, and it gives you more knobs to tune, like prioritizing different file types and stuff. But the content layer is a huge cost, and a lot of websites, maybe even most websites, are paying way too much there, in my experience. So here are some, oh, I've got my examples coming later. Yes, they're coming. So think about, when you're thinking about how to optimize at the higher levels or at the lower levels, you want to go through a workflow like this. Start by setting a quantified target. If you don't have a quantity, like 1,000 milliseconds, or each page load must be less than 50 kilobytes, or whatever, if you don't have a quantity, then by definition you don't have a problem. And that might seem obvious, but in my previous life, I did a lot of consulting where I would beg people to turn on HTTPS, and they would say it's so slow. And I would say, well, how fast is it now? And they would say, I don't know, but it's got to be as fast as possible. And it's like, well, that's true. It should be as fast as possible. But if you don't know how fast or slow it is now, then you don't know if TLS would hurt. And they never liked that answer. So then I had to draw pictures for them and give them examples. So assuming you've got a quantified target, and 1,000 milliseconds is a pretty good target, measure the status quo. And we'll talk about measuring in a moment. Where are you at now? Are you already, even without TLS, not meeting your guarantee? Well, got work to do. Or maybe you already are, and we're good, let's stay there. And assuming you're not, you can play this circle game of checking all the red squares. How many connections are you making? How many resources are you downloading? How many bytes is each of those resources? Reduce all those things. How many TCP handshakes? How many DNS lookups? I've seen sites where because they wanted to parallelize all the 50 resources they load per page load, they would parallelize it over 25 CDNs. And looking up 25 host names blew their budget before making any TCP or HTTP connections. So, well, maybe too much parallelism could be a bad thing. And again, HTTP2 does a lot of this stuff for you, but it still matters at the content layer. So do all that, measure the status quo again. How are we doing? Have we met our guarantee or not? Maybe go back. Maybe you've met a new guarantee and you'd like to tighten your quantified goal. So that's great. Obviously now you can do even better. 500 milliseconds instead of 1,000. That would be sweet. When you feel that you're happy, you can go to the green circle and be done. And then when you add TLS, you can do this exercise again. Make sure you're still meeting your budget, whatever it is. And if not, fix some stuff. So as to recap, TLS underlies all those performance guarantees, so we have to have it. And I admit, TLS is not free. Let's do I like to do this. Let's have a poll. So there's all those things of TLS, the server authentication, the data integrity, and the data confidentiality. There's a lot of crypto going on. And there's additional network traffic to do the handshake. So who thinks that the symmetric cryptography, the encryption of the data, is the slow thing of TLS? Anyone think that? Nobody thinks that? That's interesting, because everyone else on the internet does think that. They're wrong. You're all right. So Good on you. Another thing that could be slow is the asymmetric cryptography, the public-private key pairs, where you say, hi, I'm really twitter.com, and no one could, in the lifetime of the universe, falsify this guarantee that I'm about to make to you. And then the client says, well, let me just check that math. Is that slow? Any hands? Some hands. Not zero. Those of you who raise your hands are about right. That's slower stuff. It's fixable, but yeah, you're going to pay some price there. It's going to be like in the milliseconds. You'll notice it. And that's a bummer. And then the third thing that might cost us time is the network, the additional part of the handshake. Who thinks that's expensive? Many more people. And again, you are right. That's the thing. So when you're worrying about TLS, worry first about that network overhead. Worry second about that asymmetric crypto. Don't worry about the symmetric crypto. Think about it like this. We can watch DRM video, right? So it's being symmetrically decrypted and then blasted to your GPU. And nobody ever even knows that the video is encrypted because it just does not matter. So don't worry about it. So worry about the network stuff. So we can amortize those costs after, of course, working on our content layer. So what you want to do is, at every stage in that playing the red square game, keep measuring. And Chrome provides you some nice measurement tools. I'm a huge fan of the dev tools. They're super nice, as hopefully you already know. There's this network tab that tells you what Chrome is doing on the network to load your app. And I'll say app instead of site. So here's a page load. I visit the New York Times every day, and I'm always interested to see what is going on content-wise. It's very heavyweight. And before you laugh, make sure that your site isn't like this. I don't use them to pick on them. I use them because it's just a super common site that everybody visits. So we can see a couple things in this network tab. It tells us the status and type of each request, how many seconds it takes to load the page, and where in time the request happened. Here we are, 57 requests. I just visited just the front page. We've already transferred 0.5 megabyte. And whichever request we're on here, maybe it's 15, or we're toward the bottom, I guess. We're 1, 2, 3 seconds in. And we can also see how big each resource is. 4 kilobytes, 500, whatever it might be. So there's a couple good things about how the New York Times site loads. Some bad stuff. And make sure that we want to move things into the good category. So first thing, they sprited their many little icons. So obviously, if you figure there's like 50 icons there, you definitely would not want to make 50 requests to get them all. So you sprite them, and that helps a lot. So make sure you're doing that if you're not already, because the overhead of starting a new network connection for each of those would really kill you. And then TLS would look really bad if you made 50 just to get little bitty icons. So there's some bad stuff about their site that they could easily fix. First, we have here some JavaScript. It's gzipped, which is super good. Always make sure you're doing that. But even gzipped, it's still 62 kilobytes. So think about what a browser has to do to parse and execute all that code. 62 kilobytes compressed. So multiply it by 5 or 8. So pretty soon you're talking about a lot of code. And that's just one of many. Here's another JavaScript, not compressed for some reason. And it's set to never cache. It says specifically, don't cache this. Well, turns out it's often exactly the same text. So they could have cached it. And certainly they could have compressed it. So make sure you're always caching and compressing as much as you can. And here's a trouble spot that would be the kind of thing that would make TLS seem too expensive, but really the cost is elsewhere. So here's a CSS file that contains within it a base64 encoded font, and the base64 encoding multiplies it by what ratio? Anyone? 4/3. Someone said 4/3, which is true. So it's bigger than it needs to be because of how they've encoded it. And then they set it to cache for only 300 seconds. And it's 0.5 megabyte. So every 5 minutes, you're going to get another 0.5 megabyte font file. That's probably the same as it was 5 minutes ago. So don't live in this world. That would be sad. That would be slow. That will blow your budget. So in addition to Chrome DevTools, it's also good to look a layer below. Look at the TCP and DNS and IP layers. So who's used Wireshark? Hopefully some people. Good, many of you, great. So you can see lots of good stuff, including what's going on at the TLS layer in Wireshark. And I find that it's always an eye-opener. When I was in consulting world, trying to convince people that they could indeed afford HTTPS, I'd bring up a screen like this, and many eyes would open. So there's a couple things going on in this page. This one, it's a very small page load. It only took a quarter of a second to get all the packets. There's only about 18 total. We can see at the bottom, there's no visible text. It doesn't look like a web page. It's all ciphertext. And that's what you want all those ad inserting people to see, is nothing. All those people, all those passive surveillors, all those tamperers, you don't want them to be able to do it. So that's good. We can see that that's working. And then we see that the size of the packets is mostly small. There is one thing that stands out, though. The server hello, which contains the certificate, is like 2,700, 2,800 bytes, which is also about the same size as the whole web page. So that's a bummer. I would really like to amortize that cost and reduce it. So one thing you want to do is make sure that your TLS sessions live as long as possible so that you don't need to re-handshake TLS. You can, I don't know if you knew this, you can restart a existing TLS session that the client and server have already negotiated over a totally different TCP connection 5 minutes or 5 days later if either side is keeping a cache that long. So make sure that your server is configured to keep TLS sessions alive as long as possible so that you don't pay that expensive network thing very often. And so that you can get, and also things like HTTP persistence and pipelining or HTTP2 streams get the most benefit from the handshake that you do pay for. Also, you want to make sure that that initial stuff, all the setup, the TCP setup and the TLS setup, falls within the initial congestion window in TCP. If they don't, you'll have to wait just for the ACKs for your handshake. And that will slow you down badly. The good news there is that it's becoming a standard internet-wide to make that congestion window much larger. In the old bad days, that 2,700, 2,800 bytes might have blown the budget. But these days, usually, often, and you can check with Wireshark and libpcap and other tools, that you are, in fact, not blowing the initial congestion window just with your handshake, because that can be a bummer. So these days, you have a lot more headroom, maybe as much as 5,000 bytes, maybe even 8,000, and that helps a lot. But if your server certificate is really big, or the chain is unnecessarily long, or if your CA gave you a certificate that includes their logo, some of them have JPEGs of the logo. It's like, well, those bytes are wasted, and those are the most important bytes, those starting bytes. So don't get caught there. So just by looking, almost everybody, and I'd be surprised if any of you were already at a point where your app was already maximally optimized at each of the layers. So just by looking, you can discover lots of headroom where you can introduce safety. And overall, I should note that in this move to SPDY and HTTP2, in certain cases, by going to HTTPS, Google has experienced an overall latency reduction, not an increase. Even an affordable increase would be cool, but oftentimes we're actually able to do better by introducing end-to-end security and reliability. And it's good for users. So thanks for hanging out. And I'll be at the panel, I think, immediately next. There's a booth. So come yell at me if I'm wrong. Thanks.